In section 2 of the third chapter, the definitions of the 5 logical operators introduced in the first section are captured here. So our operators are dot, which corresponds to and. We have the V corresponding to or in a particular way called inclusive or. We have horseshoe, which is how we translated if-then. There's some complexities with that we're going to talk about. We have tilde or squiggle for not. And we have triple bar corresponding to if and only if, necessary and sufficient, just in case. There are other ways to put and or, as has been characterized in the first section of the chapter. Okay, now, why do we need definitions? The reason we want these definitions is so that we can determine truth value of basic claims of these types and more complex claims as well. We want to determine the truth value, for example, if I have x and y. We're giving two truth functional operators here, so the truth value of x and y is determined by the truth values of x and y. This is a pretty clear one. No real surprises or issues here, and it's true when x and y are true, and otherwise it's false. So that would be an example, but we might want to, when I say more complex logical expressions, maybe want to determine the truth value of not x and not y or z. And we'd need parentheses in there because that could be grouped in 2 separate ways. We might wonder about something like that. All right. Other reasons that we want to have these definitions are we're going to be, and these are the things that we'll go through as we continue in the third chapter, be able to point out different logical features of claims with these definitions, and ultimately, and this is the bottom line and the big point anyway, use these definitions to be able to determine and assess whether or not arguments are valid. Okay, so let's take a look at and. I'm going to write it like this. Let's say I have an and claim. I really have 4 options. Both parts could be true. So I have an and claim. Both parts are true. That entire thing. I'm doing this sort of logico-arithmetic here. True and true is true. If I have true and false, well, and requires both things to be true, so that's false. All my other options are going to be false as well, but we could have false and true. Order does not matter for and, but it does matter in some cases. If then is the one case that we're going to see where it matters, and we'll talk about that. If I have an and claim, first part's false and the second part is true, it's false. If I have an and claim and both parts are false, it's false. Okay, let's go on, switch colors here, and do or. As I explained in the book, there's definitely a very important background on this. We got our 4 options. Let's take a look. I have true or false. Writing the options in the same way, false or true. How are we going to calculate the or operator? That's our question here. All right. Now let me go with the clear ones first. If I have exactly one of the 2 expressions true, it's true. If both expressions are false, then the expression is false. If I say I have a sister and a brother and I have neither, if I say I have a sister or a brother and I have neither, then what I've said is false. If both of the things are true, it depends on what you mean by or. You could mean exactly one of the 2 is true, or you could mean that at least one of the 2 is true. And in regular language and regular discussion, often one's meant, often the other's meant. Since we don't know, unless it's explicitly said, logicians read it as just being at least one of the 2 is true. So if we have an or statement, both parts are true, it's true. If you just want to say it's exactly one of the 2, then we'll learn different ways in our language, our logical language, to say that. Okay, going on here. Let's take a look at if-then. There's some complications here as well. At some point you move beyond the theory and put this into practice, but it is important, big picture, to understand what's going on theoretically as well. And I'll just make some quick comments on that. The clear one in this case is if we have an if-then, I say if if I say if x then y, right? If x then y, and x is true and y isn't, then I've clearly said something false. Let's look over at the two cases to the right. If false, then true. If false, then false. I say if x, then y, and x isn't even true, then I'm sort of safe. All bets are off. I just said that if x is true, then y is true. Not the other way around, as we've seen, which is a different claim. And so, sort of all bets being off, we got to decide one way or the other in terms of the truth values. And so the definition we get here is true in both these cases. It only made a comment about what happens if x is true. And if x is not true, then the expression counts as true. If we say if x and y are both true, that looks good. We can come up with examples like I do in the book where it maybe looks a bit funny. But again, as a truth functional operator in terms of the truth values of x and y, that's the sensible way to go. Okay, we need a definition. All right, let's move on to not. Not is different. It's a binary operator. We just have two cases. So I can either have not a claim that's true, which is false, or I could negate or say not a claim that's false, then I've said something is true. If I say it's not the case that I'm 300 years old, it's false that I'm 300 years old, so it's true that it's not the case that I'm 300 years old. Okay, one final operator. I'm going to put it over at the right here. And we have if and only if. If and only if, right? If I say x, if and only if y, is just shorthand for if x then y, and if y then x. You might want to think about that a bit. And why, in terms of these definitions, that would be the case, as well as some of the translation kind of things. It's a good thing to puzzle over just a bit. Well, in that spirit, we have that x and y both imply one another, and if they're both true, then basically we have t horseshoe t and t horseshoe t, and that's going to be true. If I have true if and only if false, well, t horseshoe f is false, so for an and claim, a different way of putting what we've said, for it to be true, both parts have to be true. First part's false there, so that's going to be false. The flip side of this, if I have false if and only if true, that's false, not because of the if x then y, but because of the if y then x, which is going to wind up being t horseshoe f. Okay, and finally, if I have false if and only if false, that expression is going to be true, because no matter which way you go, we have a false antecedent. Antecedent is the first part of an if-then claim. Okay, so in review, and is true only when both parts are true, or is false only when both parts are false. For or, you need at least one of those true, one of the two expressions to be true. For and, we need them both true. For if then, there's only one case when it's false and the order matters here. That's t horseshoe f. Not flips the truth value. If and only if is true when both expressions right here have the same truth value, right here and right here. And in these two cases where the two expressions have opposite truth values, the expression is false.